Hello students, in this video we'll see an example of using the Gauss Divergence Theorem. Let's suppose that S is the portion of the cone z equals 1 minus the square root of x squared plus y squared above the xy plane. And adjoined with the interior of the unit circle, x squared plus y squared is equal to 1. Let's find the flux over this closed surface of the vector field, which is going to be y plus x, and then we'll have a z times y, and then an x squared plus y squared plus 4z dot d sigma. When we're asked to find the flux over a closed surface, we can apply the Gauss Divergence Theorem. And the Gauss Divergence Theorem, so by the Gauss Divergence Theorem, this will be equal to the triple integral over the interior of the cone, interior of S, of the divergence of this vector field with respect to the volume measure. Y plus x, then z times y, then x squared plus y squared plus 4z dv. So let's compute the divergence of the vector field. This will give me the triple integral over the interior of S of, this will give me a 1. So I'll have a 1 for the first term, the partial with respect to x of this. The partial with respect to, I'm going to do the x derivative of this, the y derivative of this, and the z derivative of this, and then add them together. So I'll get a 1 over here, I'll get a plus z over here, and then I'll get a plus 4 over here. So we're supposed to integrate z plus 5 dv. And just as before, let's look at what this cone looks like. So this cone looks like this. There's the z-axis, the y-axis, and the x-axis. Cone looks like this. And there's the unit circle. And so we'll put this into cylindrical coordinates. In cylindrical coordinates, we're going to integrate theta from 0 to 2 pi. We're going to integrate r from 0 to 1. And we're going to integrate z from 0 up to this cone. Well, let's see, what is z equal to on this cone? It's equal to 1 minus r. So we have that. Then we're going to have a z plus 5. Then we're going to have an r dz dr d theta for our Jacobian. So let's do these integrations. So I'm going to first integrate z. So when we do this, we're going to have the integral from 0 to 2 pi, the integral from 0 to 1, and then what? And then we'll have a z squared over 2 times r, and then a plus 5z times r, and then z goes from 0 up to 1 minus r. Then we have a dr d theta. And so plugging this in, what will we have? We'll have the integral from 0 to 2 pi. Then we're going to have a 1 minus r squared over 2 times r. Then we're going to have a 5r, so that will turn into an r, 5r times 1 minus r. And this will be a integral from 0 to 1 for the r, so then a dr, then a d theta, right? So let's this is only of r terms. The theta is going to integrate to 2 pi, so we're going to have 2 pi times the integral from 0 to 1. What will this give me? This is going to be a 1 minus 2r plus r squared. So that's going to give me a r over 2. And then we're going to have a negative 2 over 2 is a 1, so we have a negative r squared. And then an r squared times r over 2, that's going to be r cubed over 2, r cubed over 2. Then we're going to have a plus 5r, and then a minus 5r squared, so minus 5r squared dr. And this will give me 2 pi. This first thing over here is going to integrate to 1/4. This will integrate to negative 1/3. This term over here will integrate to positive 1/6. This term over here is going to integrate to 5/2. This term over here is going to integrate to -5/3. So after simplifying this long, ugly fraction, we will find our solution to the problem. So we saw that instead of having to parameterize the surface by two parts, computing the divergence gave us a function, z plus 5, which was much easier to handle than having to parameterize the whole surface, giving us great value to using the Gauss Divergence Theorem. Thank you very much.